If you travel 30 times further from the Sun, you pass the orbit of Neptune and enter a cold, dark stretch of space. This is the Trans-Neptunian region. It begins where the average orbital distance from the Sun, the semi-major axis, exceeds 30.1 astronomical units. This volume of space follows a complex dynamical architecture. Since 1993, astronomers have observed roughly 5,000 minor planets operating in this darkness. The Minor Planet Center currently maintains a catalog of 1,049 precisely numbered trans-Neptunian objects. Telescopes struggle to capture clear images of bodies this small and distant. To actually map this region, we have to stop looking at the blackness of space and start reading the raw orbital data. This table is the primary forensic tool, recording semi-major axis, eccentricity, inclination, perihelion, and aphelion. By isolating three parameters, semi-major axis, eccentricity, and inclination, we can plot these numbers to reveal invisible subdivisions. We are building a phase space map to translate rows of text into a physical blueprint. This mathematical translation is the only reliable way to differentiate a resonant object from a scattered one. It turns a spreadsheet into a planetary map. We will start our map with 15,760 Albion. Found in 1992, it was the first trans-Neptunian object discovered after Pluto, making it a perfect baseline for our data. This diagram shows the semi-major axis, the average orbital distance from the Sun. For Albion, it's 44.2 astronomical units. Next is eccentricity, measuring deviation from a perfect circle. Albion's 0.07 eccentricity keeps its perihelion, its closest approach, and aphelion, its furthest point, close to that average. Albion provides a standard circular orbit. We can use it as a baseline to measure the extreme variations found in other objects. This graph charts semi-major axis along the x-axis against eccentricity along the y-axis. Adding the data, a massive cluster immediately appears. These are the classical Kuiper Belt objects, also known as cubanos. They sit neatly between 40 and 50 AU and maintain low eccentricities. Within this group, astronomers identified two distinct populations, the cold and the hot. Orbital inclination is the key variable here. Adding a z-axis shows the cold objects forming a thin, flat disk aligned with the planets, while the hot objects orbit at steep, vertical angles. The existence of these hot orbits proves the classical belt is not a pristine disk. These high inclinations are the physical scars of historical gravitational scattering. Looking back at the 2D chart reveals sharp, vertical columns of data points. One massive cluster appears exactly at 39.4 AU, the Plutinos. The data for Pluto and Orcus shows them on this exact vertical line, their high eccentricities stretching up the y-axis. They occupy this specific distance because of a 2 to 3 orbital resonance. These objects complete exactly 2 orbits for every 3 completed by Neptune. High eccentricities bring their perihelion inside Neptune's orbit, yet they never collide. Being mathematically phase-locked ensures they are far from Neptune during closest approach. This resonant architecture repeats. At 47.9 AU, we find a second vertical spike, the 1 to 2 resonant TNOs. The 2006 reclassification of Pluto was a direct response to this data. The graph establishes Pluto as the largest representative of a dense, mathematically synchronized class. To see the full scope, we expand the x-axis from 100 astronomical units out to 1,000, revealing the scattered disk objects. Take Eris. Its 0.44 eccentricity is a result of gravitational violence from Neptune, stretching its orbit and driving its aphelion out to 97.7 AU. Further still are the Sednoids. This completely separate, detached class challenges our understanding of the solar system's history. Sedna's orbit is a paradox. With a massive 0.86 eccentricity, its 76.2 AU perihelion creates a vast spatial gap where it never approaches Neptune's orbit. Because Sedna never interacts with Neptune, its extreme orbit must have been pulled by the gravity of something beyond the known planets. The catalog also documents physical properties, categorizing objects by their albedo, or their reflectivity, and spectral taxonomy, which describes their color. Most trans-Neptunian objects have very low albedos, reflecting about 9% of light, with colors ranging from blue-gray to deep red. Mapping albedo onto our graph highlights 136108 Haumea and its family. They stand out as a major anomaly, glowing with an albedo of 0.51 against the dark background of typical scattered objects. This exceptionally high reflectivity indicates a surface of fresh crystalline water ice. Haumea's family represents the physical debris from a massive historical collision. Translating these mathematical plots back into three-dimensional space reveals the vast physical reality of the outer solar system. The architectures are now visible: the stable, flat ring of cubawanos, the overlapping locked loops of the plutonos, and the massive, skewed ellipses of the scattered objects. These orbital parameters are a fossil record. They map the historical outward migration of Neptune through the primordial disk, which permanently organized the system into these structures. This massive architecture is based on only a fraction of the total population. There are nearly 5,000 unnumbered trans-Neptunian objects currently observed, but not yet fully mapped or named. Every data point represents a human effort. From Clyde Tombaugh's discovery of Pluto in 1930 to modern automated surveys, generations of astronomers have spent their lives charting the darkness to find these points of light. The map of the outer solar system is not a finished document. It is a dynamic, evolving blueprint that we are still actively drawing today.